All right, so today we'll finish off talking about conservation of momentum, and we've looked at some examples already. One of the reasons that we're interested in momentum is because it's one way of converting power. If you attach an electric drill to this in reverse, so the movement of the sprinkler drives the armature of the drill, the stator, I guess, then you have the ability to be able to take one form of potential energy in water and turn it into other potential energy if you store it in a battery, electricity. So in other words, we can make conversions between things. And so we'll talk about rotational momentum today, but so you've all seen these things before. So these are just a few little pieces of eye candy, maybe to get us in the mood for things. I think I've taken the sound off these. I can describe what's going on. This is a guy who's taking liquid nitrogen, not very safely, so don't do this at home. Don't do it by professionals. We should probably have gloves on that left hand if I were him. And he's pouring it into a bottle. He's going to put a cap on it. The cap has two little tubes that come out of it. And so when you seal it in and you dump it in that beaker in front of him, in warmer water, the liquid nitrogen sublimates, it goes straight to a gas, it expands, and it drives a little sprinkler machine as well. So these are the tubes coming out of the top. If you angle them so that it will squirt gas, in this case nitrogen, out of them as it turns from liquid straight to a gas, then it is able to do work. So it's taking potential energy and chemical energy in terms of stored energy. There's a phase change involved, and the expansion of the gas is what drives that particular machine. So again, a rotation machine. They are used commercially, of course. And the commercial application of this is in hydroelectric dams, creating electricity from potential energy stored in water above a dam. And also, with the green revolution and solar and wind power are always intermittent. You generate electricity when the sun shines or when the wind blows, and you can't store it very easily. And so one way to do it is a pump storage scheme, which is shown here. And that is the idea that you pump water from a lower reservoir up into a higher reservoir at nighttime when electricity is cheap, and then when the demand comes to peak in the daytime, when everyone turns their toasters on at 7 o'clock in the morning in New York City, then you run it back down through to give you extra capacity. And so you can actually build less capacity into your system by using storage mechanisms like this. And a Francis turbine is merely the opportunity to be able to run fluid into a turbine. It goes in at some velocity, comes out at a different angle and different velocity also, different angle. Even if it's the same speed, it's a different velocity. And as a result of that, turns a machine such as this. I think there's a better one on the next. No, I guess that's a Pelton wheel, which you've already seen. I guess this one does go into something afterwards, okay, so you see it. So it comes down through this pipe here, goes into the turbine, and then issues out 90 degrees and comes out and becomes the downstream flow. This is the exit flow. I guess it's the exit flow. I can't read German. Maybe someone here can. Pelton wheel we've already looked at. Same principle, just a bunch of cups destroying momentum. You could imagine that if you hold that Pelton wheel static, that you have to have a torque applied to it because it's trying to twist. And if you let it go, then as we'll see today, the velocity it moves at is going to be the speed of if it's frictionless and weightless, then the velocity it moves at is the speed of the fluid which is hitting those individual cups. And this is kind of a neat one. I think this is just a cool idea, this one. And this is a self-running water pump, not to generate electricity, but to pump water. And so it's, as you'll see, it's got these silver fins on it, which is turning it, and it's just a coil which has a catcher as it goes around, which will come out of the water. So this is the catcher that fills it up, and it just, as it goes around, it screws the water into the core of the thing, and then the core discharges along this component here. So very clever, I think, very robust, simple, the best devices, of course, are the simplest possible devices, and it's very, very simple. So used to be able to pump water. Okay. So that's why we're interested in these individual things. And so that will give you a flavor for what we'll talk about. So let's do what we usually do. We talked about conservation of momentum, linear momentum last time. So let's kind of recap that. And let's then take it on to talk about moment of momentum equations. And so the first part is maybe to deal with this. So we'll talk first about linear momentum, which is this. It might be worthwhile noting that we've chosen to, so for linear momentum, we have written this, we've chosen to write this expression as something that looks like this. Where these are all vectors, and our control volume is just a block. We've drawn this block before. This is W2, this is W1 relative to the boundary, and so we've used this before. Let me write it in longhand so that we just make the case that if we write this out, this is really a collection of three equations, which look something like the relative to the boundary velocity in the x direction, y direction, and z direction. The velocity of the control surface in the x direction, y direction, and z direction. Multiplied through by the mass flow rates, and these are the sum of, so this is physically what it looks like. A scalar value, these are individual vectoral components, right, in the x direction, y direction, z direction. And forces resolved in the x, y, and z direction. And so the reason for writing it out in longhand, and I guess it's a summation of these. The reason for doing it longhand is that typically we will resolve in one direction. So for instance, in the x direction, it would be the normal to the boundary velocity in the x direction plus the velocity of the control surface, also in the x direction, multiplied by the mass flow rate across all boundaries that make sense. You're going to pre-multiply by this, so that cancels out some of the mass flow rates. And that's equal to the sum of the forces. We've made the case, I think, also in terms of this control volume, x, y, and z. Well, this could be z, I guess. We've used z for that. Doesn't matter. Then these are relative to Cartesian directions, both of these, as is this. But these are normal to the boundary. Flow rate's normal to the boundary. So that's important. So I thought we'd do a quick example, and the example I was going to do, let me split it down here, is going to be one of, there's one on the page before this idea of kind of a vane that you're hitting things with. And the question is, if you hit it with a nozzle of water and you leave it to run, it's going to run. If you hold it in place, there's going to be a force you have to hold in place to keep it static. So what are the simple representation of the expressions that you might use to represent that? And so this vane could look like this. Let's say that the velocity coming here, let's call V0. there's some velocity that goes over that boundary. We'll call this point 1, which has A1 and V1. And it comes out through here at point 2. And this is area 2 and V2. Or W2, doesn't matter. We'll talk about them in due course. So one question you might want to ask is, if this is on rollers and sitting on the ground, then what are, for instance, the velocity of the control surface in the x direction if you leave it free to move, or if you hold it in place, what is the magnitude of the force in the x direction that you want to apply to put it there? Let's call that Rx. And I guess we want to have a coordinate system, and probably the only one that is important to us is the x direction. So first of all, let's talk about steady state behavior. And so we have this expression here that we're going to attempt to use. Let's rewrite this as, this should be a summation, I guess, of all of these. So that's not particularly important. So let me get rid of this. So let's rewrite this expression as the sum of normal to the boundary velocity times mass flow rate in the x direction. So this term here and this term, plus velocity of the control surface in the x direction times mass flow rate. So I'm not really violating anything here. Is equal to the sum of the forces in x. So the reason for writing this is, if it's steady state and the mass flow rate in is equal to the mass flow rate out, so steady state implies that the sum of the mass flow rates are equal to 0, in equals out, then by definition, since the velocity of the control surface is not deforming, has to be one number, this part here has to be going to the same velocity as this part here, and this part here, and this part here in the x direction. And so this term here has to equal 0. Has to equal 0 because of this. And so if that's the case, then we have the expression is just the relative normal to the boundary velocities of the water times the mass flow rate is equal to the sum of the forces in x. And if we write that out in terms of the individual components, what other one thing we might want to do is, in this particular case, we only have one relevant component. So let's write it out for that. So what's it going to be? So in the x direction, it's going to be W1 in the x direction times the mass flow rate across 1 plus W2 in the x direction times the mass flow rate at 2 equals Rx minus. Rx is in, as we've defined it here, is in the negative direction. We could draw it any direction we want, and we just find out what the actual magnitude should be, but we've done it this way.
Can you go over again why that second mass flow rate was 0? Very fast.
Because if we have this moving at velocity of the control surface, mass rate 1 is equal to 5 kilograms per second. So the product of mass flow rate times velocity of the control surface is going to be equal to 5 kg a second times 1 meters per second, right?
Yeah.
And if this is coming out of here, what's the mass flow rate out of here? And so M2 times VCS is equal to 5 kilograms per second multiplied by the velocity of the control surface in the x direction, which is 1 meter per second. This is flowing into the system, negative. This is positive. Sum them together, and they equal. And you can do it for any, combination. So any combination has the same amount going in as going out. This is always going to be a constant amount because the body's not deforming, and so the product of these two is always 0. So that's important. So usually you can get away with using this. So I'll get rid of that later. So if we look at these, the velocity of W2 in the x direction, by definition, across here, is 0. There's a mass flow rate coming across here, but the velocity in the x direction, which is what this is 0. And then we have to figure out exactly what this relation is. For this, we can invoke the idea that the velocity static is equal to the velocity normal to the boundary plus the velocity of the control surface, right? You remember this if I just draw this little cameo. And this is velocity relative to a static observer, right? It's just a vector sum of these. And so we could rearrange this to write it as W is equal to, just take this term on the left-hand side, static minus, this is just rewriting this equation. And if I put this now in this expression here, we have static velocity minus m1. So, no, sorry. We don't have that. Static velocity minus velocity of the control surface, both in the x direction. And I'm going to write out, and the mass flow rate is equal to minus Rx. And if I expand that, this is written for point 1, right, only, and this is mass 1. So let's expand this. What's the velocity static coming into this? That's this here, right? So this is V0 minus velocity of the control surface in the x direction. Could be at point 1, but it's actually the whole thing's moving the same thing. It's static. Let's assume it's static. And let's expand this out. What is this? This is density. This is area 1. I think there's a sign that's attached to this, plus or minus. And it's a velocity normal to the boundary, which is W, right? This is the amount in or out. Yeah, it's worthwhile going through this slowly, right? So I am going to replace this W here also by this amount here. And if I write out, we end up with V0 minus VCS in the x direction, multiplied by density, multiplied by the area it flows across, which is A1. And this value of W is a relative velocity, which again is just going to be a repeat of this term here, right? So this is V0 minus VCS, control surface in the x direction, is equal to minus Rx. I did have this little thing left here, which I seem to have avoided in this last one, but let's look at what that should be. This is the normal to the boundary velocity. And so by convention, if it's flowing into something, this represents the mass flow rate, this one here. So if it's into something, this is negative. And so this term should be negative, and so we should have this here. And so if I write that more compactly, it is V0 minus VCS in the x direction. We have two of these terms, so it's squared rho A. This is a minus term in here, if you can see it. And this is equal to minus Rx. So that's the expression. I think that's the right terms. So velocity squared, density, area. I guess we could check the dimensions. So we have meters per second all squared. We have density, which is kilograms per meters cubed, and we have meters squared. And so we have meters cubed meters, kilograms over meters cubed per second squared. And if you start getting rid of terms, meters cubed go out, and you have kilograms meters per second squared, which is by definition definition of Newton, right? So it's force. So the right units at least. So let's look at, yeah, go ahead. Shout it though.
The second line?
Mm-hmm. Which is the second line? This?
Yeah. What's the thing in the beginning?
Sum of? Yeah, sorry.
Why does the m go to 0 if the other m doesn't go to 0?
I'm just going to do this properly. Say that again, please.
What happened to the VCX?
This one here?
Yeah.
This is because of this. The product, this is a constant because the trolley's not deforming, control volume's not deforming. So anywhere you take it around the boundary of this control volume, the velocity will always be a constant, so it's always a single number. And we know that for steady state, the sum of mass in is equal to the sum of mass out. So multiplying the sum of mass in times mass out by a constant number has to give you 0 for steady state. Okay? Important concept. So, yeah. So we can look at we can look at the spectrum of conditions now.
Wouldn't that cancel both mass rates, not just one?
No, because this isn't constant.
Okay.
Because here, this value in the x direction is some number. Here it's 0 because it's normal to the boundary, so it doesn't. No.
Okay, so you use W is the water? Or
W is relative to the boundary. If it's a static control volume, it's the same as the water going in. But if it's moving, it's not necessarily the same. This is our, so W is the water speed coming out of the hose on the boat. V is the velocity of the boat. If you're standing on the quay watching both of them, the velocity of the water coming out of the hose plus the velocity of the boat is what you see, which is this. All right? Okay, so go, yeah.
so shouldn't you put an E on both terms then?
An E?
Summation on both terms, just to make it clear.
Well, this is covering everything that goes across every boundary. This hasn't gone it to more than one. Here, so that we know that this is 0, so we're left only with this equation. You okay with that? With this equation, this is summing them on all the boundaries. We have two boundaries which have fluids coming across them, in and out. So they're both here. And so it's summed on both boundaries. So the two end-member conditions we could imagine, for instance, if the velocity of the control surface is equal to 0, then Rx is equal to rho, I'm just taking the equation right above here, rho A V0 squared minus. So this is the velocity. V0 is in the positive x direction, so if this is 2 meters per second, then this is equal to plus 2 meters per second squared. Area, density, negative. Means that the value of Rx So this is minus Rx. So this will give us a value of minus Rx, which is negative, which means that Rx should be positive, which means it should be acting in this direction. It's probably easier to draw it in the coordinate direction, but you can work that out, right? So one end member condition is that. The second end member condition is that, and this is the force we have to apply to keep it in place. So this is unrestricted. I'm going to leave a gap. I'm going to put a case where the force is equal to 0, where Rx is equal to 0. So where Rx is equal to 0, then by definition, if this is equal to 0, the only way this can be equal to 0, since density is finite, area 1 is finite, then is if these are equal to each other. And that is if V0 is equal to VCS. Hello? V0 is positive 2 meters a second. So the velocity of the control surface has to be moving at 2 meters per second in the right direction. And that's constructive, right? The water's moving at 2 meters a second. If it's a weightless and frictionless trolley, the trolley's going exactly the same speed and being pushed ahead of it with it barely touching it. And you could choose any value of velocity in between those or beyond those, and you could get the magnitudes of the forces that you'd have to apply for that. And so this is kind of curious because it allows us to say something about the work done. We know that power is equal to, well, what is it? Work is equal to force times displacement. Power is rate of doing work, which is equal to force times displacement per time. We call this velocity. And so, in other words, power is just equal to FV. And so if we look at these end member conditions for this trolley, the amount of work that's done by this trolley, if we look at Rx versus velocity of the control surface, we have two end member conditions. When the control surface is moving at 0 velocity, then the magnitude of this Rx is some magnitude. When the magnitude of the force is equal to 0, the control surface is going at the same fluid velocity, V0. And you could imagine there's some relationship between them. It's not a straight line. You could actually work out what that relation is just by substituting for the force, Rx, and the V, both of which you have down here. But you can see that the power here is equal to 0 because it's a finite force, but it's no velocity. And the power here is also equal to 0 because it's a velocity, but there's 0 force. And the only place where work is done is in this intermediate one, where this would be, the power would be equal to something like a half Rx, which is this value here, times a half VCS, V0, half the velocity of the water. Something like a quarter times the product of those two. And it would, so if you plotted, I'm running out of space, if you plotted, for instance, power versus velocity, it would look something like this. Because of this, and this, and this. So it's important. So in other words, you have to resist force to be able to get useful work out of it. Okay? So keep a handle on these things. Okay? So have a look at that at your leisure. Very quickly, we did it last time, but let's also just quickly mention it. We did the example with the cylinder last time, the decapitated cylinder, and we wrote the fact that the sum of relative to the boundary velocity, control surface velocity, mass flow rate is equal to force, again in the x direction. Interestingly enough, what we've talked about doing before and getting rid of this component here doesn't work here, right? Because this is a non-steady state. And that is because the sum of the mass flow rates don't strictly equal zero. Mass is coming out of here at some velocity w, but none is going back in. And so this doesn't balance. And so when you solve this one, we have to use this expression, and this term doesn't go away as the product of these two components. So that's important. And the reason for that is that we've made the case that this other case is steady state. What comes in goes out. Mass flow rate is steady state, but in this case it is not. Right? So that's important. Okay, so review that at your leisure. So let me go back and just open a new page. It's there if you need it. Go back. So let's talk about rotational behaviors. So that's kind of set the stage for what we've done. So let's look at moment of momentum. So how are we going to do this? Let's take exactly this geometry that we've just looked at. And let me flow water in here and out of here at what I'll call V theta. And again, we could call this 1 and 2. And so we know that if we push water in here and kick it out here, it's going to have a force that comes out of it. So let's make this into a arc. That is rotating around here, and that we allow this to rotate. This is some arc that we apply. This here is a right angle, and so the velocity V theta is in this direction. And let's write out our expression for, bless you, sum of velocity static multiplied by mass flow rate is equal to sum of the forces. Let's merely multiply this by radius and radius to get a lever arm. So force times a lever arm is by definition a torque. And let's also make the substitution that V static is equal to relative to the boundary velocity plus the velocity of the control surface. And if we do that, then we can write this out as a final expression, radius times W plus velocity of the control surface, mass rate of flow is equal to the torque. And so the torque is what we have to apply to be able to keep this static, which is a lever arm a force times a lever arm. And that's the expression for rotational moment of momentum that we can use. What else do we need to know? So in other words, this is going to be for our spinning system. If we draw it in this will be v theta. This is a radius. It's going around this. This will be W, which is the water rate coming out. This will be a velocity of the control surface. And a static observer will see these at some component. I guess the other components we might want to know is that v theta is equal to the rotational speed in radians a second times r. So this is radians per second multiplied by a lever arm. So 2 pi radians a second is 1 RPS. So 2 pi radians a second is equal to 1 revolution per second. So that's one other thing that we might want to know. And the other thing that we could get out of this is that we know that power, in terms of linear power, was what? Force times velocity, which is, force is Newton meters per second, which is Newton meters per second, which is joules per second, which are watts. Then rotationally, it's going to be equal to the torque times the rotation velocity. So torque is in units of Newton meters, right? Force times length times radians, which has no velocity, no units per second. So Newton meters per second is exactly the same. So this is the same as watts. So, I mean, there's a long derivation in the notes, which we won't do today, or we won't do ever actually, but this is the expression that you need. The expression that you need to account for is to also realize that the sign convention for this is that the velocity, this is only a scalar component now, right? It's out of the system. And so it's tangential to the rotation velocity. And so you have to remember that the components of these velocities are that this is in squirting out of the hole in the sprinkler, and this has to be in the same direction. So if the rotation speed is actually going in the direction of this arrow, then this would be negative, right, in this term here. And so there's a sign convention to remember. All right? So that's the expression you need. So these are the expressions you might need. Let's go back to the notes and just go through an example that uses these. So you don't need to know what cross products are. That's where this comes from. You'll see that you get an expression that looks like this. These are the three expressions we have. This is power that we've just defined, the product of torque times rotation speed, and these are the magnitudes for the shaft work. So we can do it exactly the same way with these end-member behaviors as we did for the little trolley, hitting it with the water with the hose. You either hold it in place and you generate a torque, and if it's not moving, there's no power, but you have a torque that you have to apply to keep it in place. Or you allow it to spin, and there's no torque applied, but it reaches a velocity. And no surprise, it would reach the same velocity as stuff squirting out of it. It's a bit easier than the example where you have the velocity hitting it from a static hose, because the thing isn't moving away from it. If the stuff is coming up through the sprinkler and going out through the heads, the velocity that comes out of here is always constant. It's just the flow rate divided by the cross-sectional area coming out of the nozzle. So here's the example. So you have a sprinkler, 3 heads. It comes out of the sprinkler heads. It comes up through the bottom at some flow rate, which you know. It comes out through the heads at some flow rate. If you know what the cross-sectional area of the heads are, you can calculate the velocity. And the question is, what is either the torque you have to apply to hold it in place, or the velocity that it will spin with if there's either 0 or some torque applied to it, and how do you calculate that? So this is it. This is the expression to use, that the torque is given by the mass flow rate out of the system only in this case. This is orthogonal to these directions, so this doesn't count, right? There's no component here. So the mass flow rate is just the stuff that's coming out of here. The radius of which this acts is whatever this radius is here. And the velocity that it comes out of is going to be the velocity that's aligned along this direction here. And so we can make that the magnitude relative to a static observer. We also note that W plus velocity CS is, well, actually, cloud matters by this. V static is equal to velocity out of the sprinkler head multiplied by the velocity of the control surface. That really is what needs to go in here, but I think they do it slightly differently. Let's not worry about that. So the first case is, it's not moving. Calculate all these things. So it's not moving, the control surface is 0. This velocity out is just going to be given by the flow rate out. The mass flow rate, the velocity out is just going to be given by the flow rate divided by the cross-sectional area. There happen to be 3 heads, so there are 3 areas. So the velocity out is the mass flow rate into the system. It's divided between 3 heads, and each of those heads has an area, so it gives us a velocity out of the system. So we have this. If it's aligned parallel to this circumference, then this angle theta is 0, and if it's not, the component acting along this is going to be V cosine theta, because it's aligned in the direction tangential to this. And we know what the mass flow rate is. The mass flow rate is the total mass flow rate out of the system, which is 5 liters a second multiplied by kilograms per liter. So 1,000 kilograms in a cubic meter, 1 liter is a kilogram, right, of water. And so we have everything to be able to calculate exactly what the shaft velocity, shaft torque is as a function of these. So this is the component that comes out. This is the component due to the velocity, which is mixed in here. But there's also a component that just is a mass flow rate across the boundary, which doesn't have the cosine attached to it. So it's not cosine squared. So because we know that the torque is equal to RVM. This is out of the system, and out of the system doesn't care what angle it is, it's just normal to the boundary. This one cares that it's normal to the boundary, and so this only is cosine, not cosine squared. First condition. So let's now let that go and put the shaft to 0 and do the same calculation. If we make the substitution for this expression here, then this is what we get. This is the velocity coming out of the sprinkler head relative to the sprinkler head. And so it's coming out at some angle, but relative to the tangential direction, it has some angle. So V cosine theta is it comes out at this velocity W, and so W cosine theta would be the component that's tangential to the circle. and the velocity of the system in terms of the control surface. This is the velocity of the control surface. And by definition, this is going to be the rotational speed of this multiplied by its radius, just by definition, right? So this is the definition of a velocity. If you know it's rotating at 2 pi radians per second, and it has a radius of 1, then the circumference it travels is 2 pi r in 1 second. That's really what this is. The negative is because these are a vector sum, and if it's squirting out in this direction for w, cosine theta, then the rotation rate of this is going to be in the opposite direction. And so these together cancel out. And so now if you go through the same calculation to look at defining what W out will be, this is easier than the one with the squirting hose, because as the trolley moves, the value of W changes, because if it goes faster away from you, then W across that boundary reduces as it goes faster. But here you're squirting up through the middle, and you're squirting out of the hose always at the same rate. So this is always equal to the flow rate over 3, which will give you the flow rate out of that nozzle. And if you divide it by the area of the nozzle, that gives you the velocity out of the nozzle. And if you multiply that by cosine theta, it gives you the part that's parallel, tangential to the boundary. And so if you plug and chug now with this, then you are able to, what does it do? Yeah, I guess it does two things. You have a relationship. So you could do two things. You could either hold this velocity 0, in which case you could calculate the torque you have to apply to keep it static, or you could release this shaft force, the torque, and allow it to find out what velocity it would move at. It's exactly what we did for the moving trolley. If you hold this equal to, if you make this 0, this will be a maximum. And if you allow this to move, then it will move, and it will move it exactly. These two will cancel out relative to each other, and you can calculate what this rotational speed is. And if you go through the example, you'll see it's done for a variety of different angles. So here you have the sprinkler heads. If this angle theta, this is theta equals 0. This would be theta equals 90. So for 0 degrees, the force on the shaft is this amount, and at 60 degrees, the force on the shaft is this amount. No surprising, as you rotate it around to this point, the torque that you have to apply to keep it in place reduces. Ultimately, if it's 90 degrees, how much is it going to be? 0, right? Likewise, if you allow it to rotate, you could calculate the rotation speed, and you'll find that the maximum speed is at one of those values where it's tangential to the rotation. Okay. Is it time to go already? We've still got a minute. I'm done. So anyway, so you might want to have a look at that. So it's exactly the same as before. Much easier than the case of the moving trolley. Okay, thank you very much.